Hi everybody, this is our lecture video on the chi-squared test. So again, just like the F and the T, chi-squared test is a hypothesis testing procedure. So we want to get through steps 1 to 6 and go through that process for the chi-squared test. So the one that we're going to study in our course is sometimes called the chi-squared goodness of fit test. So that's the one that we're going to be studying. There is another type of chi-squared test out there, but obviously we're sticking to this one. And this is the little symbol for chi-squared. So F statistic, T statistic, we use F and T. But for chi-squared, we're using the symbol with the chi with a little square on it. And it's actually testing whether what we see in observed distribution fits something that we expected to see. And it's really dealing with frequencies this time. So unlike the F test where we looked at difference in variability, and the T test where it was difference in the means, chi-squared is actually looking at a frequency table to a frequency table. So way back to what we did sort of in week 1 when we were dealing with that first step of group data or frequency tables. And it actually embedded into it when you're coming up with this expected distribution deals with other types of distributions like a uniform or a Poisson distribution, and we'll get into that sort of piece of it as we look at the different types of questions related to the chi-squared test. So again, let's walk through the theoretical steps and then we'll move into doing a few examples of it. So step 1, your hypothesis statements, and these are always the same. So our alternative is what we observed is different than what we expect, versus our null hypothesis observed is equal to what expect. We don't talk about one or two tails in terms of a chi-square. It's really just looking at frequency table to frequency table. Step 2, our level of significance is 5% unless we know otherwise. Step 3, our critical value is going to come obviously from our table, where the degrees of freedom in a chi-squared table is n-1, where n is no longer the sample size, but it's capital N where we're dealing with the number of categories we break things down into. So when you look at an original frequency table, it would be like your apparent limits or your real limits or your categories if you're looking at sort of categorical data. Drawing a sketch, it's sort of right skewed in terms of a chi-square distribution. We start at 0 and work our way through, and as usual, we'll create a critical region with our critical value from the table corresponding to alpha. If we make it into this critical region, again, it's where we reject our null hypothesis. So that's been the same for our last few tests as well. And again, that will always be the same sort of procedures we look at. Step 5 is where things sort of deviate in terms of all of our hypothesis procedures. So the F test was the ratio of larger variance over smaller variance. That T was that sort of big square root formula that we dealt with. When we're dealing with the chi-squared, my suggestion is to set up your data basically in a chart form. So this is our test statistic right here. It's the summation. Remember, sigma means sum of observed minus expected squared divided by expected, where your O is your observed frequencies, your E is your expected frequencies. Obviously, the ones that you observe are usually the easier ones to find because those would be the ones that you collect as a technician. But the expected are where it's a little bit more challenging to come up with those values, and we either use a probability or some other relationship that we know from previous studies. So, as usual, if we make it into critical region, we reject. So let's walk through some sort of different types of questions that we'll see in terms of the chi-squared goodness of fit test. So here's our first question. So a forester expects the distribution of trees in a particular maple forest to be 20% red maples, 25% Norway maples, and 55% sugar maples. So that's some kind of expectation. So this is what we've expected to see. This is what previous studies have shown. And then the next part of that question is, a student conducts a survey and counts in a particular lot 30 red maples, 33 Norway maples, and 77 sugar maples. So that's what we basically observe. And our question really is, at a 10% significance level, does the forest match the forester's conjecture? So basically, is what we observed the same as what we expected to see, or is what we observed different than what we expected to see? So again, it's a chi-squared distribution that we're going to be working with our chi-squared hypothesis test. So step 1 is our null and alternate. So observed equal to expected and not equal to expected. Step 2 is alpha. In this case, it does say 10%, so we'll go with 0.10. Degrees of freedom, remember, is capital N minus 1, where N is the number of categories that you break things down into. So when I read through the question, you can see that we basically have those 3 categories: red maple, Norway maple, and sugar maple. So I'm going to say 3 minus 1 is 2 degrees of freedom. Okay, so at 2 degrees of freedom, now we're going to go look that up in our table. So when we ran the F test, we looked up in the F table. When we ran the the T test, we looked at the T table. If we're running the chi-squared test, we're going to run with the chi-squared table. So let's pull up the chi-squared distribution. So I'm looking at 10%. So alpha along the top is 10%, and we want to go 2 degrees of freedom. So I'm getting a critical value of 4.605. So 4.605. Step 4, visualize, sketch it in our picture. So here's 0 and our critical value of 4.605 up here somewhere. That corresponds to a probability of 10%. And then step 5 again is where sort of our tests deviate, and that's when we want to come up with our test statistic. So the test statistic for chi-squared test is that chi-squared is the summation of O minus E squared divided by E for each of our categories. So that's why setting it up in a frequency table is a little bit easier to see, because then you can sort of go through the steps of actually coming up with one of these for each of our categories. So I've set up sort of in my 3 categories and then filled in my observed column. So this is what we would observe. So we looked at getting 30 red maples, 33 Norway maples, 77 sugar maples. So if you look at sort of a total of that, we looked at 140 total trees coming out there. That's what we'd like to sort of take a look at your N value, and we want to see if that is equivalent to some expected frequency. And the expected is where sort of things are a little bit tricky when you come up with what your chi-squared expected column is. This one in particular gave us proportions or percentages. So we thought that we should get around 20% red maples. So of the 140, we would expect 20% or 0.2 of the 140 to be red maple. So 0.2 times 140 gives me 28 trees there. And then for Norway maple, we expected 25%. So 0.25 of our total 140. So 35. And finally, for the sugar maples, we expected 55%. 0.55 times 140. So 0.55 times 140 equals 77. So we observed 30, we expected 28. We observed 33, we expected 35. We observed 77 sugar maple, and we expected to see 77. So again, what the chi-squared goodness of fit says is this distribution about the same as this distribution. They look really close to each other, but again, that's what we're hypothesizing, so we're running a test about it. So these ones, remember, should add up to the same 140. They have to be the same N value in order to do the chi-squared goodness of fit test. So you have to have your distributions the same. And then it really just becomes the mathematics around plugging into our formula. So I sort of have my column set up in 3 steps. O minus E would be my first step, square it, divide it by E as we sort of go. You can jump all the way to the last column if you want to. It doesn't really make a sort of a difference mathematically. I'm just sort of going to do the 3 steps as we go. So 30 minus 28 gives me 2. 2 squared gives me 4. and then 4 divided by my expected value of 28. You can leave it as a fraction if you want to. If you want to actually do the decimal answer, 4 divided by 28, then keep at least 3 decimal places until the end, as always a good rule of thumb. So 0.14, and I'm going to round to 143. Now then the next one, 33 minus 35 gives me a -2. -2 squared gives me a +4 again. 4 divided by, in this case, 35. Gives me a 0.114. And then finally, sugar maples. So 77 minus 77 gives me 0. 0 squared gives me 0. 0 divided by 77 gives me 0. So notice that as they get further and further apart, then these numbers get bigger and bigger for that final column. And if they are exactly the same, you're going to get a chi-squared value of 0. So we start to drift towards that critical value. So when we add these guys up, that's our chi-squared value. So we end up getting, in this case, 0.257, which again is really close to our 0 line here. So 0.257, definitely not in our critical region. As usual, we do not reject our null hypothesis. So I'm going to get rid of this just because it's a little crowded in there. So step 6, same as always, defend our conclusion. So the chi-squared of 0.257 in this case is less than my critical value of 4.605. So not in the critical region. Chi-squared is not in the critical region. So do not reject null hypothesis. Do not support your alternative. So in the end, we wanted to cancel this out, we couldn't, so we have no support that we have a difference. So in the end, no significant difference in what we observed versus what we expected. So to answer the actual question, yes, the forest does seem to match the actual conjecture of what happened before. So different sort of way of coming up with our conclusion, whatever way you sort of want to write it. First thing I'm going to do is express the expected versus observed. So there is not a significant difference in the observed trees and the expected trees. The forest does match what we thought originally, what the forester expected. All right, so let's see a couple other types of examples. So this one was actually giving proportional relationships, so looking at a proportion or percentages. But there are other ways of coming up with the actual expected values, and sometimes you use a different sort of distribution. So a couple distributions that we're going to talk about in our course. The first one is a uniform distribution, meaning all observations are equally likely to happen. So if you have n categories, then we're going to have an equal probability of 1 over n for each of our categories. So that's uniform, everything equally likely. The other one is what we call a Poisson distribution, and it actually comes up with a random expected column based on some kind of expected value. And again, Poisson is not really one that we're going to sort of look at the curve or look at the values and how to come up with them. If we ask you to do a random distribution, those will be provided. The uniform, though, is pretty straightforward in calculating. You look at your number of categories and then you make it a ratio out of that total. So let's do a practice question on each of those. We'll start with the random distribution one. So here's our next question. So in an area of 120 kilometers squared, We have 29 kilometers squared with no drumlins, 16 kilometers squared with 1, 20 kilometers with 2, etc., etc. And this is our question. So using a 0.05 level of significance, are the drumlins randomly distributed over the 120 kilometers squared area, or is there a significant difference between what observed and what is expected? So what we're doing is sort of dealing with same kind of thing, a frequency table to frequency table. And instead of actually having a list or proportional relationship, we're going to talk about that random distribution. So in the column down here, these were randomly distributed around some expected value. And then obviously we have our counts for what we observed in terms of the kilometer squared. And we're going to run a chi-squared distribution on it, or a chi-squared hypothesis test. So let's start at step 1 again. So our hypothesis statements, null, alternative. So we would like to see if what we observed is different than what we expect, and the null is that what we observed is the same as what we expect. Step 2 is alpha. So it does specify in the question 0.05. But we would assume that otherwise anyway. We don't talk about cutting. There's no sort of indicator of doing that. Step 3 is degrees of freedom, which is capital N minus 1, where N is the number of categories. So it might be easy to look down sort of in our chart here. We have 1, 2, 3, 4, 5, 6, 7, 8 categories. Notice we do have a 0 in there. So it ends up being 8 categories. So 8 minus 1 gives me 7 degrees of freedom. Let's use these two pieces of information to find my critical value. So let's go to our chi-squared table. 5% at 7 degrees of freedom. 5%, 7 degrees of freedom gives me a critical value of 14.067. So let's sketch that out. 14.067. Step 4 is the sketch of my picture. Starts at 0, 14's up here somewhere. And we have an area of 5% or 0.05. And step 5 is where that table comes into play. So we've already sort of set up the table already here. So observed, all our observed values, they add up to the 120. The expected values from the Poisson distribution, again, add up to 120. These have to be equivalent to each other. And then again, to save a little bit of time, just because this is a bigger chart, we have our O minus E squared divided by E. So you could check if you wanted to each of those. So it would be 29 minus 10 squared divided by our expected value of 10. So we could do that again in our calculator if we wanted to. So 29 minus 10. Make sure you hit equals there to get a value. Then you can square it and divide by 10 in this case. So divided by your expected value. So that's how we're getting it for each of our categories. And then we're really adding up at the end to get our chi-squared test statistic. So 36.1 plus 3.24 plus 3.90 plus 2.46 plus 0.25 plus 0.5 plus 5.33 plus 25 gives me a chi-squared value of 76.78, which is definitely way up in my critical region. Even the first one passed my critical region, so we didn't really have to do necessarily the add up, but we'll do the full procedure obviously. But we're definitely in the critical region, and we are rejecting our null hypothesis here. So chi-squared of 76.78 is greater than my critical value of 14.067, therefore reject the null hypothesis and support our alternative. And so what we're doing is we're rejecting our null and we're supporting that there is a significant difference in my observed versus expected. So if there's a difference between observed and expected, these are not randomly distributed. So in that case, there's some kind of geological situation that's actually happening here, why they're not randomly distributed. So there is a significant difference between the observed drumlins and the expected distribution. The drumlins are not randomly distributed. Okay, so that's an example of when we use the random distribution using the Poisson generator. Let's look at one where we're talking about equally likely to happen with the uniform distribution. So here's our practice question. So we go birding and we look at different bird species with the frequencies listed below. So when we were out there, we saw 13 red-winged blackbird, 8 American goldfinch, 9 common loon, etc., etc. And we would like to test at the significance level 5% if the bird species population sizes appear to be uniformly distributed. So are we equally likely to see a red-winged blackbird, equally likely to see American goldfinch, equally likely to see a common loon, etc., etc. So again, we're running a chi-square distribution because we're looking at counts versus what we expect to see. So let's start at step 1 again. So step 1, our hypothesis statements. So what we observed is not equal to what we expected. Observed is equal to what we expected. Step 2 is alpha, and in this case we're going to use 0.05. Step 3 is degrees of freedom, which is capital N minus 1, where N is the number of categories. So we have 1, 2, 3, 4, 5, 6 different categories that we classified into. So 6 minus 1 gives me 5 degrees of freedom. We'll look up our critical value, 5% at 5 degrees of freedom. So 5% at 5 gives me a critical value of 11.070. Step 4, sketch our graph as usual. And that corresponds to an alpha of 5%. And then step 5 is our test statistics. So we've drawn the line, our pass-fail region, so now we have to test it out. So first off, let's just see how many birds we actually observed when we were out there. So we had 13 plus 8 plus 9 plus 9 plus 6 plus 15. So we looked at a total of 60 birds. And what we would like to do for the expected column is to say that, is it uniformly distributed, right? So that's that equally likely to happen. So what you basically do is you just take your N value and you split it into how many categories that you actually have. So in this case, we have our 60 broken down into 1, 2, 3, 4, 5, 6 categories. So it works out nicely. 60 divided by 6 gives me 10, 10, 10, 10, 10, 10. So that's what it means to be equally likely to happen. We just basically take our total that we have and then cut it into how many pieces we have in terms of our number of categories. And then it becomes our math piece. And again, this table is sort of set out to do each step individually. So 13 minus 10 gives me 3. 3 squared gives me 9. 9 divided by 10 gives me 0.9. 8 minus 10 gives me negative 2. Squared is 4. 4 over 10 gives me 0.4. 9 minus 10 gives me negative 1. Negative 1 squared is 1. 1 divided by 10, 0.1. Same thing for the next one. 6 minus 10 gives me -4. -4 squared gives me 16. 16 divided by 10 gives me 1.6. 15 minus 10 gives me 5. 5 squared is 25. 25 divided by 10 gives me 2.5. And then we basically have to add them up to get our chi-squared value. So we end up getting 5.6. Come out there. Okay, so did we make it into our critical region? No, we did not. So as usual, do not reject our null hypothesis. There is no significant difference in observed and expected. So this column and this column are not significantly different. So even though they look different, the numbers are different, remember, it's not a significant difference when we're looking at sort of a hypothesis testing procedure. So chi-squared of 5.6 is less than my critical value of 11.07. Do not reject null hypothesis. So do not support your alternative. There is no significant difference between observed birds and expected. And my expectation was that they were uniformly distributed. So no difference between the observed and expected. Therefore, the bird species are uniformly distributed. We are equally likely to see sort of each of the categories or each of the different birds that we're looking at.